We were looking at the differential equations, or we started looking at differential equations with non-constant coefficients, and this is a typical second order equation for which we have the solution where a0, a1, etc. were constants. And if you go ahead and do the algebra, which we did, we find that we get polynomials as the solutions. And if you look at the Taylor series also is going to tell you that if a function is infinitely differentiable, then you end up with some kind of a polynomial. And all of these polynomials, e to the x, sin x, cos x, were appearing as solutions to the constant coefficient differential equations. And therefore, what we say is that if I have got now an ordinary differential equation which has got non-constant coefficients, then maybe I can go ahead and assume that a polynomial solution is going to work, and we'll say that px and qx are polynomials or analytic functions. And we said that an analytic function is one whose derivative exists and the function also exists. And if the derivative exists and if the derivatives exist at a particular point and the function exists, then it is called a regular point. So if you have a function px or qx and you say that I am able to get the derivatives of this particular function and it is existing at a particular point, then you say that it is a regular point. However, if you say that the function is not analytic at x equal to some number x naught, then you say that you have a singular point. So we'll be looking at singular points and ordinary points, and in addition to being singular, if the point or the function is such that x times px or x minus x naught times px and x minus x naught square times qx become analytic, then it is called a singular point that is regular. And if this does not satisfy or this condition is not satisfied, then we call it an irregular singular point. Now, if you've got an ordinary point, then you can get a solution. If you've got a singular point, then you get a solution. If it is a regular singular point, if it is an irregular singular point, then a solution does not necessarily exist. We are not going to be worrying about irregular singular points. We are not even going to be worrying too much about regular singular points, and we'll see why. But we first try to understand what is this regular singular point and irregular singular point. And we just took a couple of examples. And the first one we said was that is the px is x, the qx is unity. So these are differentiable functions and they are existing at x equal to 0. So the first fellow is a regular point. There is no singularity associated with that point. Then we took another example, and this example you just cast it in the y double prime plus px y prime plus qx y equal to 0. And so you have got a 1 by x, a 1 by x square. At x equal to 0 there is an issue. So we call it a singular point. But then if you multiply x with x and x square with x square, you get a function which is analytic, which means that the function exists and the derivatives exist. So therefore that is a regular singular point. The last example shows you what is an irregular singular point. So you've got y double prime plus y prime by x plus y by x cube. X equal to 0 is a singular point, and if you multiply this with x, the first function, which is px, which is 1 by x, then you get analytic function. However, the next term, even though you multiply it with an x square, there's a 1 by x hanging in there, and that makes it a singularity, which means that even after multiplying px and qx, if either one of these comes out to be a singularity, then we say that it is an irregular singular point. Okay. Alright, so we then started by looking at an example, and the first example we saw was for an ordinary point. We never quite completed it, so we'll do that today. So we said that there's an equation which is y double prime minus 1 plus xy equal to 0. So this is the equation that we want to solve, and the earlier methodologies that we have are going to give us trouble. So what we say is we are going to now go ahead and try and attempt a series solution, and we said that this is a hypothesis. We say that y is going to be equal to 0 to infinity Cn x to the n, and y prime is going to be equal to 0 to infinity n Cn x to the n minus 1, and y double prime is 0 to infinity n into n minus 1 Cn x to the n minus 2. So we have hypothesized that y equal to Cn x to the n is going to be a solution, and we plug that into this differential equation. So y double prime, we can plug it in. This is n minus 1 Cn x n minus 2, limits are 0 to infinity, minus 1 times y, so the y is summation of Cn x to the n, 0 to infinity, and then minus of x times y, so x times y is Cn x to the n plus 1, again 0 to infinity. Okay. So all that we have done is said that the solution is going to be y equal to Cn x to the n, and then plugged it into the equation. Okay. And now we try to say that we would like to simplify this guy, or we would like to add these guys up so that we get some kind of a compact solution, maybe. And to that extent, we had said that we are going to make n minus 2 equal to m. We just say that we are going to replace the variable, which we can do. And in which case, when n equal to 0, m becomes equal to minus 2. So this is minus 2 to infinity. This term I am just putting it there. And this becomes n is m plus 2. So n is m plus 2. N minus 1 is m plus 1. And then n is m plus 2 and x to the power of m. Okay. So this term we have just simply rewritten it like this. We'll just leave this guy alone because there is nothing funny about this guy. And again, this next guy here, we'll just say that I'm going to replace this n plus 1 with somebody called k, and n plus 1 equal to k, so you have got c, n is k minus 1, and then x to the power of k, and then this guy, when n is equal to 0, this guy goes from 1 to infinity. Okay, so this is where we were when we quit last time, and so we get rid of this guy here. So now what we say is, I've got all these guys, they all look a little bit different, but we would like to homogenize this particular equation so that we can add up these guys. Okay. So this guy goes from minus 2, this guy goes from 0, this guy goes from 1, and so we would like for everybody to go from the same limit, the smaller limit to the higher limit, so that we can just club the whole terms, or club all the terms together. Okay. So towards that now, let us just say that this guy is 1 to infinity. Right? This guy is 1 to infinity, I can't do very much with this guy. Okay. So 1 to infinity, and this guy is 0 to infinity, so I can say that, okay, I'm going to split this guy into two terms. One is c0 x to the power of 0, and then I say that this is cn x to the n 1 to infinity. Okay. So this limit I'm trying to make it equal, and if this is all the same, then I can just go ahead and add up these terms. Okay. So I've got this extra guy who is hanging in there. So let us just write this guy in the at the bottom. So you have got, this is minus, and then we say c0 x to the power of 0. Okay, so that's my first term in here, and the second term is up there. Okay. Now this guy here, we can just now say this goes from minus 2 to infinity. I would like this guy again to go from 1 to infinity, and keep the same thing, m plus 2, m plus 1, c m plus 2, x to the m. Okay. So how many terms more should be here? 3 terms more, because minus 2 term, so m equal to minus 2 gives me minus 2 plus 2, which is 0, minus 2 plus 1 is minus 1, and then you have got c of m, this is c0, and then this becomes equal to m equal to minus 2, right? And then I have got plus another term which is minus 1, minus 1 plus 2, minus 1 plus 1, and then this guy is c1, right, x to the power of minus 1. Okay, and then I have got, now this guy is 1, minus 2, minus 1 and 0. So this is 2 times 1 times 2 x to the power of 0. Okay. So these are the additional terms which are there. Okay. So this was what Professor Puranik had commented on last time, saying that you're going to get these guys with x to the minus 2, x to the minus 1, and then at that time we had remarked that, okay, let us just brute force go ahead and see what happens. Okay. So what you see now is, this guy is 0, so this guy drops off. This guy is also 0, so this guy also will drop off. Okay. So everything is now consistent. So there is a small amount of discomfort in the sense that if you say that d dx of c is equal to 0, right, I can say that d dx of c is c x to the power of 0, and x to the power 0 is 0 x to the power minus 1, and therefore it appears to be having some kind of a problem, but really there is no problem, at least from an engineering perspective. Okay, so the first two terms are gone. I have got 1 to infinity, I have got 1 to infinity, and this guy also now is 1 to infinity. C, now I can replace k with an m because this is just a dummy index there. Now can I add these guys up? There's no problem, right? You've got all the limits are going from the same. All of this guy is going there. So we'll just add up everybody together. So what you end up with is, so I can get rid of the summation sign and just say that I'm going to get rid of this also. I'm going to get rid of this also. I'm going to get rid of the summation sign. Everything can be done now. And then I've got this term minus this term minus this term is equal to 0. So what we get is Cm plus 2 is equal to Cm plus Cm minus 1 upon m plus 1 m plus 2. So this is what the algebra is going to give us. So this is valid for what m? For all m? M goes from 1 to infinity. Remember that we have gotten rid of the summation 1 to infinity. So my m goes from 1 to infinity. Okay. So this guy goes from 1 to infinity. This is what is called a recurrence relationship. For the simple reason that you are not doing everything or getting each term separately. It's some kind of a recurring number or recurring relationship, so that you just put m equal to 1, 2, 3, 4, 5, 6, you are going to get C2, C3, C4, whatever you want. We still have this guy here, okay, that we have not yet done anything about, but let us just say that if now this guy, so this guy also has to be equal to 0, right? So this becomes x to the power of 0 is 1, x to the power 0 is 1. You have got C2 or C0 is equal to twice C2. This implies C0 equal to twice C2. Okay. So that's another relationship that we have. So we've got two relationships. One is C0 equal to 2C2 is one relationship, and another is a whole bunch of relationships which are going from for m equal to 1 to a large number, okay, whatever that number may be. Okay. Okay. So if now we go ahead and use this relationship, there is a C0, there is a C2, there is no mention about C1, so let us try to see if I can do something with a C1. So this, let us see m equal to 1, suppose I put m equal to 1, I get C3 is equal to C1 plus C0 upon 2 and 3. Okay. So this is C3 I am getting. Okay. Similarly, I can go ahead and get C4, C5, blah, 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 which means, remember what was our original objective? Our original objective was to get a y, which is going from 0 to infinity, Cn x to the n, and now we have all the Cn's we want, right? Do we have all the Cn's we want? Do we have all the Cn's we want? This relationship is giving me what? Everything. Just now we wrote C3 in terms of C1 and C0, right? And C2 is obtained in terms of C0, okay? Similarly, if I say C4, I don't want to do that. So m is equal to 2, so C4 is going to be coming out in terms of 2 and 1, right? So everybody is known to me except 1 and 0. Okay, C1 and C0 are still unknowns. Okay. So we started with y equal to Cn x to the power of n, and we said that the differential equation was given to me. We did all this algebra and we got now all C's except C0 and C1. Okay. Okay. So is that something which is comfortable or not? I had a differential equation. I said that I have an infinitely large number of unknowns in this equation, and I did a lot of algebra and I came up for a lot of these unknowns, but two of these unknowns still are unknown. So have I done anything good or not? I mean, you just had infinitely large number of unknowns. You said everybody is known except two guys. Now, did that solve anything at all? Yes. Why? Remember, I started with a second order equation. Okay? And I never said anything about the initial or the boundary conditions. Okay? Second order means you need two conditions, which means that it is not surprising that I have a solution which has got still two unknowns hanging in there. Okay? Remember, even earlier on when we had y double prime plus a1 y prime plus a0 equal to 0, we had c1 e to the power of some lambda x plus c2 e to the power of lambda 2x, right? So these c1 and c2 are always going to be there. You need other conditions which you are going to be getting from somewhere else that is going to permit you to go ahead and get the final solution. Okay. Alright, we'll do a couple of more examples and then we say that we understand this business of series solutions. Okay. Another example that I'm going to now look at is somewhat of a, I mean, it's kind of like beating it to death, but nevertheless I would like to do that because this is a fairly nice equation. Okay. So this, of course, you can do. You can, now we have the recurrence relationship C3, C4, C5 dot dot dot. You can go ahead and obtain it, and you're going to get the final solution in terms of C0 and C1. And you can evaluate your C0 and C1 using the initial or the boundary conditions. Okay, we take one more example. Okay, so this is 1 minus x square. The procedure is exactly the same, but that's all right. Minus twice xy prime plus L into L plus 1 equal to 0. And this is so-called Legender's second order differential equation. Okay. L is a parameter that should be given to me, and we'll see what that means, or to some extent at least. Okay. So let's just do the same thing again. We have got y, we have got y prime, we have got y double prime, and I say that I'm going to take this here, so y double prime, which is going to be summation of n into n minus 1 Cn x n minus 2. I have an x square here, I multiply it with an x square, and I get rid of this minus 2. So this is one of the terms. Okay, and then plus 1 times y double prime plus summation of n minus 1 Cn x to the n minus 2. Okay, so that stays. So that's my first term, minus twice, and then I have got my y prime there now. In the previous example there was no y prime, and this is x to the power of n. okay, L plus 1y, and then plus L into L plus 1, and then summation of Cn x to the power n equal to 0. All that we have done is just brute force algebra, nothing else. Okay, so we have plugged in the y equal to Cn x to the n and the associated derivatives into this equation, and we have written up this guy here. Okay, so once again these are all going from 0 to infinity, 0 to infinity, 0 to infinity, 0 to infinity.
So what y prime is n minus 1 there?
Pardon me? Y prime is n minus 1. I have multiplied it with an x, so I have thrown the minus 1 out. Okay. Anybody have any trouble with this equation? We have come from here to here, and subsequently it is just brute force algebra, nothing else. Okay. We just need to come from this guy here down by using those upstairs. Okay. Anybody have any trouble at all? Okay. So it's just brute force algebra that is happening and nothing else. So we have taken this guy here, and now what's the next step now? What would be the next step? What would I want to do now? I would now want to add up these guys somehow to get some kind of a recurrence relationship, right? That's my goal. Okay. I don't want to get the constants all one by one. So we say we would like to somehow get a recurrence relationship, and therefore we would like to modify that equation so that I'm going to get something useful. And we should have, if we want to somehow get something under a summation sign, I would like to get the same x quantity here and the same limits here, and then I can just go ahead and add up and get some kind of a recurrence relationship. So that's basically what we are going to be doing. So again, what we say is, we take this guy here and substitute m for this guy here. Okay, so n minus 2 equal to m. Okay, so n minus 2 equal to m, you take this guy here and then again do the same algebra. Okay, that now I'm not going to do on the board, but up to here is fine, and then you just go ahead and say that I'm going to substitute n equal to m plus 2 or n minus 2 equal to m. That would be a more proper way of putting it, but nevertheless both are identical to each other. So just go ahead and plug this in and you get this guy here, and now what you see is that everybody is going from 0 to infinity, 0 to infinity, 0 to infinity. Okay, so you can go ahead and say that, okay, how did I get this 0 to infinity? Is it 0 to infinity? When I put this n minus 2, that's the only thing I'll point out here. We said that we are going to put n minus 2 equal to m. So n minus 2 equal to m, so this guy becomes m, this guy becomes m plus 2, this guy becomes m plus 1, m plus 2, and how is it that I got still 0 here? Is there a mistake here? No, correct. So how is it that I have just simply not bothered to change this guy here in this next step? So what would this guy be? What would this be? What is the bottom limit? 0, right? I am saying n minus 2 equal to m. So if n is equal to 0, what happens to m? Minus 2. Okay. I should, strictly speaking, put minus 2 here, right? Now why am I putting 0 there? Because the first two terms are 0. Okay. So if I take minus 2, this guy is minus 2 plus 2, that is 0. And then when I have minus 1, this guy is 0. So there is no problem in changing it to 0. That's all you need to understand. Okay. Is that clear? Okay. Okay. So rest is just algebra. Okay. You can just go ahead and do the algebra, and what you get is, I'll just write down the final result. So it's fairly straightforward. Just group the terms together and you are going to get Cm plus 2 is equal to m into m plus 1 minus L into L plus 1 upon m plus 1 m plus 2. Okay, times Cm. And again remember, the limit is going from 0 to infinity, so m is equal to 0, 1, 2, 3, dot dot dot. Let's get rid of this guy now. Alright. So now what are the unknowns in here? Remember, the original equation had an L, we never said anything about the L, and let us assume it is an integer now. Okay, so L has to be given to me. L has to be given to me because that's something that I don't know. That was there in the equation, we just plugged it in. So let us say L is equal to 0, just to start with. Okay, L is equal to 0. Then what happens here? M goes from where? M goes from 0 to infinity. M has nothing to do with L. So M goes from 0 to infinity. So let us plug in a 0 here. M equal to 0. So C0, right? C2, sorry. Okay, M equal to 0. So this becomes equal to C2. This M is 0. 0 into 0 plus 1 minus this is 0 times 0. Right? Okay. What is C4? What is C4? What should I do to get C4? M is equal to 2. I plug M equal to 2 and then I get a C2 sitting in here, and C2 is already 0. So what is C4? C4 is also 0, right? So this guy is 0. So C4, C6, everybody is going to go to 0. Okay. Now there is this C1 now. Correct? So C1 is going to be equal to what? Sorry. So now you put M equal to 1. So M equal to 1 will give me C3 is equal to 1 into 1 plus 1 upon 1 plus 1, 1 plus 2 times C1. Okay. And you can get C3 is so much times C1, C5, etc., etc., etc. But so what you are therefore getting is the C0 was there, and then C2, C4, etc. were all zeros, correct? So I have got the solution as being equal to, provided L is equal to 0, if L is equal to 0, suppose L is equal to 0, then I got a C0 and then C2, etc. were all zeros. I got a C1 and then a C3, etc., etc., etc. Remember what we said, this is a second order equation, so I need two unknowns, right? So I've got a y is equal to C0 plus C1 times that, right? So what we are saying is that I've got two terms here. One is a C0 and then I've got a C1 which is there, which is an infinite series. Okay. Okay, just bear with me for one more time. Okay. So that is for L equal to 0. Okay. Now you can go ahead and do it for L equal to 1. Okay, I have done it for L equal to 2. So L equal to 1 you can do it. Similarly for L equal to 2 you can do it. So let us do it for 2. Again, now the recurring relationship is there. I don't want to do it on the board. So if L is equal to 2, what you get is, now let us see, L equal to 2, let us say. So L is equal to 2 and this gives me C2 as equal to minus 6 by 2 C0. Okay, you can do the algebra. Algebra is all given here. So you can go ahead and do the C2 just like what we did for L equal to 0. Do it for L equal to 2 and you will get C2 equal to, okay, might as well do it. M equal to 0 in that equation. So C2 is equal to M equal to 0, L equal to 2. So M equal to 0, L equal to C2. Okay. This is 0 minus 2 into 2 plus 1 upon M equal to 0, 1 into 2. Okay, so that's what you see there. 6 divided by 2 and then there is a C0 sitting there. So C2 is equal to minus 6 by 2 C0. Okay, that is C2. Now what happens to C4 now? What happens to C4? If I plug into that same equation, C4 is with M equal to 2. And if I put M equal to 2 here, if I put M equal to 2, what happens to the numerator? L is 0. What is the numerator? M is equal to 2, L is equal to 2. So 0, right? So C4 is equal to 0 times C2. This is the so-called recurring that is happening. Okay. So C4 is equal to 0 C2, and what can we therefore say about C6? C6 is equal to, M is equal to, right? M is equal to 4, correct? So 4 plus 2 is 6, and then on the right there is a C4, so C6 is equal to 0, and all these other even terms are going to go to 0. Only 2 even terms have survived. Which are the 2 even terms which have survived? C0 and C0 plus C1 x plus C2 x square plus, this was my solution, right? C0, there was nothing you could do, C0, and then we will write a C1 here. What is C2? C2 is minus 6 by 2 and x square plus what? What are the even terms now? Plus C4 x4, C6 x6. What is this term? 0. What is this term? C4, C6, etc. are all zeros, right? So if they are all zeros, what happens to these terms? They are all gone. Okay, so you have got C0 times 1 minus 3x square plus C1 times x and all those other terms. Okay, so what you are getting is C0 1 minus 3x square plus C1 times a whole bunch of terms. Okay, that is when L equal to 2, and so on and so forth. If you do the first term which is there, which is C0, which was for L equal to 0, and then C0 times 1 minus 3x square, which was for L equal to 2, and then for L equal to 1 you would get a C1x, and so on and so forth. Okay, one term has got a finite length, if you will, the other term is an infinite length, right? This guy is finite, this guy is infinite. Similarly, this guy is finite, this guy is infinitely long. These finite terms together make up what are called the Legendre polynomials. Okay, so apart from that, as far as this course is concerned, we are not going to be interested in the Legendre polynomials. Okay, all that I am trying to tell you is that the Legendre polynomials are going to fall out as the solution to a second order differential equation. Later on we will see Hermite polynomials, Chebyshev polynomial, everybody falls out as solution to a second order differential equation. Okay, so the Legendre polynomial, so you have got like this, and similarly now if you go ahead and keep on doing, you can do it for, so I have just plotted this out. I mean, it looks nice to plot it, that's why, apart from that nothing else. So I have taken the different polynomials that I got, and if you make the magnitude equal to 1 on the right hand side, all these polynomial coefficients which you have are what are called the Legendre polynomials. So the Legendre polynomials are coming from the second order differential equation. Okay, we're going to talk about this later on a little bit, not a whole lot, but okay, so far what have we done? We have taken ordinary points. Okay, now remember I have just plotted it from -1 to 1. Okay, -1 and 1 not included. If I include -1 and 1, what happens to this equation? This at x equal to 1, what happens? Can I still use the solution? What kind of a point is x equal to 1? What kind of a point is x equal to 1? Okay, this guy is what? 1 minus x square y double prime minus twice x y prime plus L into L plus 1 equal to 0. The first thing that you need to look at is, we said that this is an ordinary point. Why is it an ordinary point? This is minus 2x upon 1 minus x square plus 1 by 1 minus x square L into L plus 1. What is x equal to 1? Is it an ordinary point or a singular point? It's a singular point, right? So the solution that we just got is not valid. Okay, outside of x equal to 1 it is valid. Okay, so what we have done and not explicitly said was that we have obtained a solution between +1 and -1, excluding those 2 points. Okay, those are singular points. Okay, so the next thing we say is, now we have solutions to ordinary points, or if I've got a second order equation, y equal to x to the power, y equal to summation of Cn x to the n works for ordinary points. We have seen a couple of examples. The first one was a general example, second one was the Legendre polynomials which were coming out of that equation, but x was not equal to 1. Then it's fine. Okay. The next case we will see is what happens if you have a singularity. Okay, so if you have a singularity, then this does not work, and we need some additional math to worry about it. We are not going to prove this, we are going to only state it and see how to use it. Okay. So there's something called the Frobenius theorem, and it says that if x naught is a regular singular point, okay, so if I have got a singular point or I have got a singularity at a particular point, and we have already seen that a singularity can be a regular singularity or an irregular singularity. Okay. So if it is a regular singularity, then the Frobenius theorem works. If it is irregular, a solution may or may not exist. Okay. Alright, so we are only going to talk about regular singularities or regular singular points, and what the theorem tells is that the solution y is going to be, again a series solution, is going to be some Cn x to the power of n plus r, okay, where r is some number that needs to be determined. Okay. So the Frobenius theorem tells me that this guy goes from, so just like in the previous case, you say y is going to be summation of some an x to the n, but now you say that it is an x to the n plus r. Now who gives us r? We will see in just 1 minute. Okay. Alright, so if now, suppose I have evaluated r, okay, and I have a second order equation, I will get 2 r's, and if r1 minus r2 is not an integer, r1 minus r2, this is the theorem, okay. So if r1 minus r2 is not an integer, then I can get 2 solutions easily, there is no problem, okay. The solutions are y is summation of x r1 and then some bn xn plus r2. So the solutions are clean. You can get the solutions y1 and y2. There's no problem with that. Okay. But if you have got r1 minus r2 as a positive integer, right, the 2 series solutions may not exist. Okay, they may exist, but they may not exist. And if y1, so the larger root, see, I have got 2 roots for that equation, which is going to come from solution of r, and r1 minus r2 is a positive integer, which means I am going to take r1 as the larger root. So y1 equal to an x to the n plus r1 is going to be a solution. Y equal to b n plus r2 may or may not come out as a solution. Okay. So that's why we say that y2 is equal to this, a could be equal to 0. So if y is equal to b n plus r2 is a solution, then a is 0, otherwise a is going to exist. Similarly, if r1 is equal to r2, then this is the solution. And this is very, very similar to that Cauchy-Euler equation which is there on your home assignment, and we are not going to go ahead and try to even say anything about these solutions. We will just say that this is the theorem and we are going to religiously follow this and try to get solutions. Okay, we are not going to prove this theorem per se. Okay, another important point is a0 and b0 are non-zero. a0 cannot be equal to 0. Just keep this in the back of your mind. Once we are taking an example and moving ahead, that's when we are going to be seeing why this should be the case. Okay. So as of now, there is this thing called a Frobenius theorem, which we are going to be using to see if there is going to be some kind of a second order equation with a singularity in it, regular singularity, then we use the Frobenius theorem, go ahead and try to get a solution. Okay. Alright. Again, we'll take a famous equation and try to apply the so-called Frobenius theorem and see where we get. Okay, so we have already seen how to handle a ordinary point, and now we are looking at a singular point, and this is an irregular, it's a regular singularity. Irregular singularity we won't even want to touch. So let's say I have got x square y double prime plus x y prime plus x square minus mu square y equal to 0. This is the equation that we are starting with. Okay. All right. So what is this x square? So let us put it in our standard form, x square and x square. Okay. So this is 1 by x. Okay. So there is a singularity, right? There is a singularity because at x equal to 0 things are blowing up, and there is a problem with the analyticity of this function, right? So whenever you are having x to the minus 1, take the derivatives also don't exist at x equal to 0. Okay. All right. So let us say that we have a equation which has got a singularity. So how do we find out whether there is this is a regular singular point or a irregular singular point? What do? You take this is px, right? Multiply this with x, right? And take this guy and multiply this with x, multiply this guy with x square. Okay. So I multiply this guy with, this is q, multiply this guy with x square. Okay. So what happens to this guy here? Px is 1 by x. So this is 1 by x. 1 by x times x is 1. So is 1 an analytic function? Yes, right? It exists, derivatives exist, and there is no issue at any point. And we have to say that we are trying to look at the solution at, let us say, x equal to 0. Okay. All right. What about this guy here? Qx times x square is what? What is qx? This is qx. Qx times x square is again x square minus nu square. This nu is some number, let us say, as of now. Okay. So this guy is analytic. Analytic means what? It should exist. Derivatives should exist. So does this exist? Okay. We stop here for today. I'll see you again tomorrow.